Okay, hello. We will start with recording chapter 10 session. So this is an attempt to record chapter 10. Um, I hope you guys can hear me during this recording. Since I'm just here by myself, I'll go ahead and enlarge the screen. Okay, chapter 10 is about quantity, relationship, and chemical reactions. So chapter 10 is essentially the end of chapter 8 and 7. So, chapter 8 and 7 built up and prepared us for chapter 10. We talked about balancing the equation, different types of reactions in chapter 8, balancing the equation, doing simple conversions within the same formula. In chapter 10, we're looking at what we saw in chapter 7, but in the context of a chemical equation. Okay, so the chemical equation does show relationships between the formulas in the chemical equation. So let's go right into it. I will skip over the pages that do have goals. I won't go over that. It's very wordy. Feel free to read it at your own time. And I'll go straight to this slide right here. Slide 5. So we're told, imagine a balanced equation, a chemical equation. In the balanced equation, there is a relationship that exists between the formulas in the balanced equation. So I'm going to be looking at this balanced equation right here, and I want you to see that we do have 4 different formulas, 2 of which are reactants, and then 2 are products, right? These 2 on the left here are reactants. These 2 on the right are products. So if you have a balanced equation, there exist relationships, numerical or quantifiable relationships. So some kind of number relationship between any 2 formulas. So in this case here, we're told we're focusing on the coefficient. The coefficient, these are the numbers that we use to balance the equation. And previously we talked about the coefficient being used to describe a relationship between the chemicals in the balance equation. Remember, there's 2 ways, actually, there's more than 2 ways. I want to focus on 2 ways of describing the amounts of the chemicals in the balance equation. One way is to look at the molecular relationship or particulate relationship, depending on the type of formula you have. The one that we have here, since this is a compound, so I use the symbol C for compound. This is a compound. This is an element, but a special element, right? Remember the ones that have a subscript of 2, the ones, the Brinkelhoff, these are diatomic elements. So I'll just call this D E for diatomic elements. And then right here we have a compound, and then we have a compound. When we're trying to describe the amounts of these formulas, and we have the following types of formulas, right? You have compounds, and then you have one diatomic element. You can use the term molecule, molecule for all the compounds, and then of course molecule here. Okay, well, what do we do with the element? It's kind of tricky with the element. If the element is diatomic, remember the diatomic, we talked about this before. The diatomic elements, the ones that exist as molecules, remember those? Those were the Brinkelhoff, Brinkelhoff. And you can see where oxygen is part of that Brinkelhoff group. These are described as molecules. They're not really called atoms. The individual atoms, 2 atoms of oxygen, make up 1 molecule of oxygen. So here, the term you use is molecule because you don't just have 1 oxygen, you have 2 of them. So molecule. Okay, so after that little history of what we learned in the past, now you can use the number and these names to describe the amounts. You can say 4 molecules of ammonia, 5 molecules of oxygen, 4 molecules of nitrogen monoxide, 6 molecules of water. So what they did here, after kind of, they didn't really explain all that, but I'm here to explain all that. Now they're trying to relate two quantities in the balance equation. And by the way, in this chapter, you will see a consistent theme throughout, which I noticed in chemistry, very thematic. In the whole chapter, when we're doing a lot of calculations, we're focusing on relating two components, two formulas in the whole balance equation. Okay? So here they're relating the two reactants. I can see that. And you have 4 molecules of NH3 relating to 5 molecules of oxygen. Okay? And this is, oh snap, I dropped something. Oh, I should be fine. This is a particulate relationship. Remember, particulate is a term that describes chemicals at the level of atoms and molecules. Okay? So, these two can then be written as a ratio, which is right what we have right here. Now, you can relate any two formulas in the balance equation, regardless of the number of formulas you have in the balance equation. Of course, you need to have at least 2 different formulas, right? Okay. You can also use the mole level. And with the mole level, I think they use the mole level down here. I want to say the mole level. With the mole level, you will use the same number, but in the place of the word molecule, you will use mole. Now, disclaimer, mole is not the short form of molecule. They're completely different terms describing different things, okay? So 4 moles of NH3 and then 5 moles of O2. Okay, so what I'm going to do here is I'm going to digress a little bit. I'm a little rusty in doing the lectures because it's been a while. It's been a whole, how many? 4 weeks of no lectures. So I'm a little rusty. Okay, so I used to confuse moles and molecules because I don't know, in my head I'm thinking MOLE or even MOLS and then molecules. It looks like a short form, right? And it was used interchangeably. But please note, we described this before. Moles or moles is an amount. It means a lot. Okay, it means a lot. I heard a new word recently that was describing a huge number. And that number was so huge, I was like, you know what? I can't deal with this. That's just too huge for me to relate to. But a mole is a very, very huge number. So a mole refers to an amount, right? And the amount is Avogadro's number, 6.022 times 10 power 23 items of whatever, okay? Versus a molecule refers to a structural formula. So when you have elements combined together to form a compound, that's a molecule. So this is the units that we're counting. So many of these make moles, right? It took me a while to wrap my mind around that. I'm like, but the words look similar, but they don't have the same meaning. They have completely different meanings. This is describing the compound created by the elements combining versus this is describing how many of these or whatever it is you're counting, okay? Very, very many. So hopefully that clears the confusion. Remember, you could also, in the same balance equation, you could also relate, let's do product on product, right? We could also relate NO to H2O. So we'll have 4 moles of NO, and that goes with 6 moles of H2O. So of the two relationships, I'll tell you right now, the more popular one that's used that I see around is the molar relationship, not the molecular relationship. This tends to be more common, not necessarily product on product, just moles on moles. Okay, so the way we're interpreting the balanced equation is by looking at the molar amounts versus the molecular amounts. Now, please note with the balanced equation, you could also have maybe, I'm trying to think of a different kind of compound. If this wasn't a diatomic element, it was only an element, you wouldn't use, if it was just O and it wasn't O2, you wouldn't use the term molecule. If it was just O, you would use the term atom. Okay, so atom refers to a single element by itself. And then molecule refers to, the molecule of an element refers to atoms combined together, sometimes in twos, sometimes in fours, sometimes in eights. Some elements do that, okay? So just realize that. Okay, so now I want to move on, and we're trying to get to the math part. Here we're being told that apparently there is a conversion factor from the chemical equation. So apparently the chemical equation contains within itself a lot of information, right? When I was trying to make sense of chemistry, I used to think of the chemical equation like the bottom line of a recipe. If you're trying to make cake, they tell you, take flour, add sugar. It's been a while since I made cake too. Take flour, add sugar, add eggs, beat it up, do blah blah blah. So you know that when you see the ingredients together, some cake is about to be made, right? And so of course when you have the lab instructions, that tells you how it's going to be made. So for me as a student, the balanced equation was kind of a shotgun recipe. Okay, mix this amount of this, so 4 moles of NH3, mix it with 5 moles of O2, and you get 4 moles of NO and 6 moles of water. This doesn't tell you how. If you want to know how to actually mix them together and then how to capture these products, then you need a lab direction, and they have, part 1, part 2, and then all the details, right? So the balanced equation tells you what to mix, in what physical state, and what product to expect, right? We have our reactants to the left, our products to the right. Now that we have this here, let me go ahead and see. We're being told here the balanced equation doesn't only tell us what chemicals to mix and what products to expect, it also gives us something called a conversion factor. Now in chemistry, a conversion factor is a means to an end, right? Like it says here, it's for converting. Once again, that word thing, for me, conversion factor didn't really click at first. I'm like, okay. But later on, I'm like, it just makes so much sense. A conversion factor is a tool. It's a tool that's a means to an end. It helps you to convert. And in this context here, you're converting units. You're converting amounts of measurements. Most of the time, you're converting from grams to moles, or even from moles to moles, right? But the conversion factor is the tools, is the key that allows you to go from one unit to another, okay? So we're going to start simple. Our goal here is to get conversion factors from the chemical equation, balanced equation. So let's go back to this chemical equation right here. Let me actually copy this out. And then let's see. Once again, I'm a little rusty. After going over lectures a lot in the semester, you get in the groove, and I'm kind of out of the groove because I haven't done a lecture in a long time, but that's okay. Okay, right here. Okay, let me see if I can remember the features of this. There, good. Enlarge that. Okay, so before I look at this question, once again, I'm trying to get some conversion factors from here. So we did the first two last time, right? This and this. I want to mix it up. Now I want to go reactant and product. So I'll say 4 moles. I'm sticking with the popular one, right? 4 moles of NH3 goes with 4 moles of NO. Okay? Or I could go this and this. Mixing it up again. 4 moles of NH3 goes with 6 moles of H2O. Now, this format, this way I wrote it, is not necessarily useful. We want it in a fractional form. So in this case here, it doesn't matter how from where I am, it doesn't matter how I write it. But when you're looking at this in the context of a question, you see how it matters. I can write this as 4 moles of NH3 in the numerator position divided by 4 moles of NO. Okay, and down here we have 4 moles of NH3 divided by 6 moles of H2O. So you ask, right? Well, which one goes up? It all depends on the big picture, what is given, right? Now that we know how to take a balanced equation and then get a conversion factor out of it, let's use the tool we just picked out from the balanced equation to actually convert. Let's see our tool in action. So for that reason, I am going to erase all this work I did. When you're watching the video, feel free to rewind. Okay, now I'm going to look at the question right here. In context, if 3.0 moles of NH3 react, hold on a second, I'm going to look at my balanced equation. It said 3.2. I was just given 3.20 moles. Okay, I'm going to leave the E out. It's okay. Scientists use either. Okay, that's why I go back and forth. I'm trying to really adapt the whole MOL life, but my brain prefers the MOLES. I don't know why. It's a conflict. Okay, I've just used this number of NH3. React according to the equation below. Yep, that equation. How many moles of water? Okay, how many moles of water? So in my balanced equation, let me tell y'all, okay, in my youth, I struggled with this chapter because I didn't realize that in the conversion, we're working towards stoichiometry. In the conversion, there were just two main players. And I had to pick the main players from the balanced equation. So I was kind of just going around, not really knowing what I was doing. I was following the teacher, and I couldn't check my work with confidence. I was always trying to ask for assurance because I didn't know what I was doing and if I was doing it right. Okay. In the conversion, we usually have two players. One is the given, which is the given one. So I label that over here. One is the wanted, which is the wanted one. I label that over here. And for this particular conversion, I'm only going to be focusing on these two formulas. Do I recognize there's more? Yeah. But in my conversion, only two players are key. Okay. Now I write my conversion, like dimension analysis. So I write what's given first, 3.20 moles. Do not leave the units out because the units drive your action, your next move, right? I want to say it's like chess, but let me tell y'all, I can't play chess, so I shouldn't really say it's like chess. But in this case, the units drive your next move. So if you leave your units out, then you have no move, and then the game is over. I don't think chess works like that, okay? Since I have moles, oh, I forgot one more thing. I'm trying to build better habits, y'all. Work with me here. Okay, I'm doing better. Once again, I'm a little rusty. 3.20 moles of NH3. Okay, so I got the units and I got the formula. Since I have moles of NH3 here, then I'm going to have a number on the bottom. So diagonally across from my number that I wrote from this right here, I need to have another measurement that has the exact same units and formula. So some number, I have no idea what it is yet. I'll figure it out in a little bit. But it has to have the same units, moles of NH3. So we're trying to go from moles of NH3 to moles of water, and our conversion factor technically comes from the balanced equation. So I write myself a little note right here, okay, that the balanced equation holds the key to my conversion. So I read the coefficient from the balanced equation. You see this number right here, 4? It goes down here, 4 moles. And remember how we had that a conversion factor from the balanced equation? We're essentially doing that again. So 4 moles of water, 4 moles of ammonia down there, and then we have 6 moles of water right there. So I just use this right here. Remember, this balanced equation is the conversion factor we were practicing a minute ago. That's really the only conversion factor that I need. How do I know that? Because the units up here cancel out with the units down here, and the answer I get will have the units moles of water. Okay, now I'm going to pull up my handy dandy calculator. No, I don't want to do head math. And then multiply this out, divide this out, and I have 4.8 like they do. Okay, so this is a balanced equation conversion factor. Okay? So, what have we learned so far? We learned, let me keep this short and sweet, to convert from moles given to moles wanted, comma, use conversion. Oh my goodness. Brain and hand work together. This is what happens when you stay up late. Okay, the truth. Till 3:30 working on syllabi. Yeah, y'all. It's like I'm in school again. Use conversion factors from balance equation. Yeah. So to convert from moles given to moles wanted, use conversion factors from balance equation. So this is how it will look. Template, right? You will have your moles given, and then you have your balance equation conversion, and then that will give you your moles wanted. Okay, remember the numbers here have to be molar amounts. The units up here have to match the units down here so they can cancel out to give the units here. The units here have to match the desired unit. This has to be desired. The units here have to be or have to match the given. Okay, so the given here matches the given here, and then it ends up with the desired being the one that remains, and that becomes the most wanted. Okay, so y'all saw how I worked it out. So moving on. Oh, they kind of give that to you over here. Only they use the term particulate quantity. We're just going to be doing ours in moles. Amount in moles of the reactant, mole ratio from the balance equation. I call this BE. Okay, you see later on why I call it BE, because I like to just kind of do a review of the process, right? Amount in moles of the reactant, amount in moles of the product. And do you see this double-headed arrow? This means you could be going from left to right or from right to left. Okay, then we have this active exercise. So this is what I want to warn y'all, okay? Normally, this part is not given. So you want to view this question from the point of view of only the top part is given. What does that mean? That means they want you to actually write your own balanced equation and stuff, okay? Okay. I don't know what I'm copying, but we'll see. Add a page. Yeah. Okay. How many moles of oxygen are required to burn 10.11 moles of ethane? Okay. So we have C2H6 grams plus oxygen. Okay. Well, you guys have the benefit of being able to remember in the previous chapter that when you're burning any kind of fuel, you actually are doing a combustion reaction. So this and this gives you CO2 plus water. In combustion reactions, you usually get CO2 and water. Okay. And so you complete the reaction by saying, make sure you balance it. I won't spend the time balancing it, so I'm just going to copy from up here to 7. Yeah, I'm trying not to spend too much time with the balancing since we covered that in the previous chapters. Yeah, complete balance. We got that. Okay, now this is a question. How many moles of oxygen are required to burn 10.11 moles of ethane? How many moles of oxygen? Oh, my wanted was given to me first, but it's still what I'm looking for. So that is the wanted. What are the units? Moles. So my wanted is in the units, moles. And then they're saying are required to burn 10.11. So the given here is 10.11 units, moles. Okay. So I'm going from technically given number 10.11 moles to wanted moles. Okay. Once again, since I'm going from moles to moles, I'm going to be doing a mole to mole conversion, right? And it's between these two formulas right here, ignoring the other two, even though they're part of the balanced equation. So I'm going to write 10.11 moles of C2H6. Here's the thing. You're writing the given moles. You do not need to be looking at the balanced equation just yet until you're done writing the given moles. Don't write 2 here. You will confuse yourself, okay? Don't write anything there. So it's in the next step where you actually look at the balanced equation and draw information from there. This is where you look at the coefficients. So here's where you look at the 2 that's right here and write it down here. This is the only time you look at that, okay? So 2 moles of C2H6. And over here, you put 7 moles of O2, right? Since we want moles of oxygen, I'm like, let me check real quick. Do I have moles of oxygen up here? This is usually where you want your wanted units to be. Is it where it needs to be? Check. Do these units match these units right here? Check. All I have to do is the math right now. So I got 10.11 times 7 divided by 2. Yeah, 35.385. Too many sig figs. 35.39. And this is going to be moles of O2. Okay. So here's the thing. You want to make sure you know how to write this down. As usual, as you're going through the lesson, make sure you're taking notes, you're highlighting and all that stuff to help you remember what you're doing. The more organized you are, the easier it is for you. Because I feel like as a student, I made a lot of mistakes. The teachers never told me all these other non-chemistry behaviors will actually help me in chemistry. Maybe it didn't affect them, but for me, it was necessary, okay, to be organized. So here's the thing, right? Now we're saying, okay, moles to moles conversion, that was a warm up, okay? That was just you getting ready. The real conversion, the real stoichiometry, the full story is mass to mass conversion, okay? So let me show you this. What we just covered, the moles to moles conversion, is technically the core of stoichiometry. We just covered this. And we say to go from moles of given to moles of wanted, you need one conversion. That one conversion goes right here, where you get it from the balanced equation, BE. But they're telling you there's more to the story. The story starts before moles of given. It really starts at mass of given. So some problems may give you mass, and if they give you mass, you have to start here. You can't skip and start here, right? So they call this the conversion path, or I heard per path, weirdly enough. I didn't get it. You know, being a student and being a teacher is different, right? Because when you're a student, there's a lot of anxiety that comes with, I'm going to fail this class. Y'all, I understand. Like, I hear words, but I don't understand what's going on. But now I look at it, I'm like, it makes so much sense because I figured it out. I did the work though. But it's called a path because it's kind of like a highway that you're taking to get somewhere. So they call it a path, you know, like a road. You're going from one place to another. So you're traveling, right? The question they give you tells you where to start in the path. This is a whole journey from the left all the way to the right. But sometimes you're not going the whole journey. Sometimes you're going, I'll call this the first path, the whole way from mass given all the way to mass wanted. If that's what you're doing based on the question given to you, to get from mass of given, the left, to mass of wanted, the right, you would have to go through 3 conversions. It's like 3 huge steps. And each step, each conversion transitions you to the next step. The first conversion here I like to call PT, periodic table mass or molar mass. Okay, PT, molar mass. Second one, balance equation conversion, right? Last, PT again, molar mass. Is this deja vu? No. Okay. So if you're going the full path, you get to the full path by going through these conversions. The first conversion, PT of molar mass, transitions you, helps you advance from where you're starting, mass of given, to moles of given. But that's all it can do. It can only get you from here to here. That's it. Okay? Then you need to go from the second point to the third point. For that, you need your balanced equation conversion factor, the one we just learned from the coefficients in the balanced equation, right? That also only gets you from here to here. Now, how do you get from moles of wanted to the end? You use another conversion of the periodic table, which is the molar mass. Okay, now that I've shown you guys this, depending on the question, sometimes the question doesn't have you go all the way. Sometimes the question starts you from not the beginning, but kind of the middle. They may start you from right here, and this becomes your starting point. So I'll call this 2. And then you go from modes of given all the way to the end, mass of wanted. Well, you know what you need to do, right? If your goal is to go from modes of given to mass of wanted, you're trying to go from this to this, you use balanced equation. Don't use PT again. PT won't help you go from modes of given to modes of wanted. Only balanced equation is your secret key, your secret weapon to move from modes of given to modes of wanted. You catch what I'm saying, right? And then finally, from modes of wanted to mass of wanted, you use PT. I have seen some questions take you just one step to the end, and you're like, seriously? Yeah. But the thing about chemistry is this, right? Which it took me years to figure out. I say years because in my country, we studied chemistry in middle school. First year middle school, barely hit puberty, bam, there's chemistry. And like, what is going on, right? So it took me years to figure out the rhythm of it. Chemistry is a problem-solving class. That being the case, we don't just learn one way of doing things. We learn so many ways of doing things because the goal is for you to be skilled in solving problems different ways. I've had students ask me, why don't we just do things one way? And I'm like, chemistry is about problem solving. So the more ways you know, the better. That's why they mix it up. There's one way, all the way. There's another way, the shorter way, another way, the short test way. And you have to figure out in the question, are they asking you to go all the way? Are they asking you to go halfway? Or are they asking you to go really short way, right? Okay. So let's put this in practice. Oh, they write it in words here. How to do it. Change the mass of the given to the amount in moles. Change amount in moles of given to amount of moles in wanted. Change amount of moles of wanted to mass. Okay. Same thing that we just saw there. I feel like this one down here is more useful. Specific application. Oh, I like the red more. It's brighter. Okay. Once again, look at your question, analyze your question, and ask yourself, where is my starting point? If your starting point is right here and your end point is right here, guess how many conversions you need? 3. PT, BE, PT. You see how smooth that goes? PT, BE, PT. Did I have this when I was going to school? No. I wish I had this. I mean, I still got good grades, but it took a lot of work to get those good grades. A lot of years in the library. Okay, PT, BE, PT. Now they're telling you can go from here, right? Like this. Let's call this the main highway. You can go from here to here, or they can give you a different starting point. And this is a path that starts from the side and joins that main highway. Let's use blue. So this starts here, joins the main highway, and it can go to the end. Remember, chemistry is about problem solving. So the more different ways you know how to tackle a problem, the better, right? Or they can mix it up and have you start from this, go to this, and come down here. Okay? I'm keeping it simple because even though I've shown you all the paths here, we as a class will focus the main highway. And then for those of you who are trying to go into J, if you take it with me for all the other minutia ways, the other, I don't know if I use the word right, the other random ways in the other class, okay? But we'll stick with this main pathway for this class, which is either you're going all the way or you're kind of going this way, or even just the middle conversion right here, right? From most to most. We'll stick with that one in this class versus involving this other one here, okay? Okay, so here in our questions, and I went through the slides and I realized that they're giving you more than one way of the same thing. Here's the other thing, right? They're asking you what mass in milligrams. So I like to write notes when I'm reading and stuff. Since I'm using an ebook now, I can write on it and not feel bad. Before I started using ebooks, I still write on books. And you know a book is mine because I write on it. It helps me to not only focus but to process the information. What mass in milligrams of nickel 2 chloride? So you have to remember the formula of this. If not, look for the formula. Okay. Nickel 2 chloride. So what mass, this is what is wanted in milligrams, right? So this is helping me to kind of summarize what's being asked. So when I look back, I know what I'm looking for. What mass is the in what mass in milligrams of nickel 2 chloride is in a solution if 503 milligrams of silver chloride, so this is silver chloride, and this is 503, this is my given, right? 503 milligrams, okay? It's precipitated in the reaction of silver nitrate and nickel 2 chloride solution. Wow. Okay, so here's the thing. They give you a lot of information here, but what I want to focus on is the balanced equation. I tend to tell people that when you see all of this wording here, let me go ahead and copy this wording over to the next page. What you really, the balanced equation really anchors all the wording. So I always encourage people, please get your balanced equation and then look over your question again. And the question is a little bit overwhelming. That's weird. Yeah, sometimes Blackboard does that. I kind of heard a little bit of a feedback there. But okay, let's see. So I'm going to put this here and let's write our balanced equation. Once we write our balanced equation, it will help us to put the pieces together in the right place. Okay, so apparently they're asking for the mass of nickel 2 chloride. So there's nickel 2 chloride in here. And then we're given the amount of silver chloride. But it says in the reaction of silver nitrate. So technically, silver nitrate is reacting with nickel 2 chloride. So the reactants are silver nitrate, okay, and nickel 2 chloride. These are the starting material because it says in the reaction of. Yeah. Okay, so over here, it says what mass. Okay, so this is what we're looking for. What mass? We're looking for this in milligrams. And then we're told that silver chloride is precipitated. So the product here is silver chloride. And just in case you're wondering, how is I supposed to know that? They did give you a balanced equation. I saw it somewhere. Here it is. It's just kind of in all of this stuff, right? Here's your balanced equation. You already have it right here. And then you have nickel nitrate. Oh no, the I disappeared. Okay, there. Nickel nitrate. Okay, this is aqueous. This is solid. Okay, so to balance this, you put 2 here and then 2 here. So I know that we want the mass of nickel 2 chloride. I got that. And then what was given was the mass of silver chloride. Oh, given is right here. 503 milligrams. Okay. So our conversion is between those two formulas. Those are the two formulas of the four that we're going to be focusing on. This one here and this. So I'm going from here technically to that. Okay. 503 milligrams silver chloride. And then I have, I'm figuring out what this is. Okay. Now remember, we're doing a mass to mass conversion. So I'm going to write it differently, y'all. I'll write it. We're going from mass given to moles given to moles wanted to mass wanted. Okay. Here is the tricky thing, guys. Here is the trick. This is the conversion path we know. I don't know what I just did right now. Okay, let me write this over again. This is a conversion path we know. I can write it a little smaller. Mass given. I'll write it like that. Moles given. Moles wanted. Mass. Let me erase that. I need the space on the right. Mass wanted. Okay. So remember, from mass given to moles given, we need the key, secret key, periodic table conversion. From moles given to moles wanted, secret key here, balanced equation. From moles wanted to mass wanted, again, periodic table conversion. What we saw before, mass given had the units grams. Moles given had the unit moles. Moles wanted has the unit moles. And then mass wanted had the unit grams. In our question, we don't have grams, though. They gave us milligrams. What does a milligram really even mean? Remember, milli stands for 10 power negative 3, right? So what we're going to do here, I know this is the first time we're working on this. As I'm thinking about it right now, I think about things differently when I'm actually doing a presentation. I think about things more deeply. It would have been easier for us to work this problem out without dealing with the milligrams, right? Actually kind of works itself out, but I'll deal with the milligrams since that's how the question was asked. 503 milligrams. So milligram, I want to convert it to a gram, right? To convert this to a gram, 1 gram is what? 1,000 milligram. You can use that conversion, or you can say 1 milligram is 1 times 10 power negative 3 grams. Either one works, okay? The more common one is 1 gram is 1,000 milligrams. Okay, so here. So that case, 503 divided by 1,000. What happened to my 5? 503 divided by 1,000. I have to press this calculator. 0.503 grams. So if these kind of units overwhelm you, don't check out. Just convert it to a unit that overwhelms you less and then deal with this. Okay? So since this is grams, we can now start here. We're now ready to start here. And I'm going to write this as, I'll have to convert it back in the end, right? 503 milligrams is the same thing as 0.503 grams. So now I can start here, okay? As I start, I will check off the step I have completed. Okay, I will write 0.503 grams of, what was the formula? AgCl, starting point. Yes. Okay. Oh yeah, periodic table conversion. So for this one here, we haven't even had that conversation, right? What does this mean exactly? For this part here, you'll be writing the mass of, you'll be calculating, not just writing, but you'll be calculating the mass of 1 mole of that formula. So up here, I'll write 1 mole of the formula here, AgCl, okay? And then I'll figure out the grams, the molar mass from the periodic table. Please realize, in the periodic table, when they call those masses molar mass, where do you think the molar comes from? Molar comes from the fact that the mass you're seeing there is the mass of 1 mole. So that's why we use the word molar mass to just say this is the mass of 1 mole in the amount. So if you got 1 mole of the elements, whatever the formula is, you got 1 mole amount and you weighted, that's what you're getting. So all of these masses that we write down here are the masses of 1 mole of the formula, whichever formula we're dealing with. Okay, back to this. So AgCl, I have to figure out what 1 mole of AgCl weighs. My periodic table. Where are you, periodic table? Please don't fall. I'm gonna be buying a desk soon because we recognize that my desk is too small. That's why I have a lot of stuff. And then yeah, anyway, found it. AgCl, AgCl. I found Ag. Ag silver is 10. I'm kind of rounding this up. So 108 plus Cl. Cl is 35.45. 35.45. Okay. So in 1 mole of AgCl, we have 143.45. Did I make that? Yay! Barely, right? 143.45 AgCl. This is my periodic table conversion. Okay. I am looking at the future of the way I'm writing, and I see that I'm gonna run out of space in no time at all. Hold on. Oh no. Okay, hold on. I'm trying to make this smaller because my handwriting is naturally so big. Oh, come on. Work with me. Okay, this might work. Let's see. Oh. Yeah, it's harder for me to write small. It's a thing, right? I had to learn to write big because I'm a teacher, and then now I have to write small. Okay, so we got that part. Now the next part, remember, is BE because it's PTBE, right? In the BE, I have to look at my balance equation. Where is it? Right here. And look at my coefficients, right? So silver has 2, nickel has 1. So I write here 2 moles for silver, AgCl, the whole formula. This part is done. Done. And then 1 mole NiCl2. Done. Okay? So BE is done. Am I smiling? Yes. I'm sorry, y'all. I love this stuff. Okay, next. Where are we? Finally, so we have gone from here to here. We've done this, we've done this, we've gone to this. This is where we are right now. We're trying to do our last conversion. We have to do this conversion right here to get to mass of wanted. So we need the other PT. Now, if you're wondering what do I use next, remember the units have to cancel out. Grams of AgCl, grams of AgCl, mole of AgCl, mole of AgCl. Now, whatever our next move is, the mole of NiCl2, nickel 2 chloride goes down here. And then, of course, the grams of nickel 2 chloride goes up here. Okay? So remember, periodic table, the masses there are called molar mass, implying the mass of 1 mole. So this is always 1 mole. Let me tell you all what I used to do. Did I understand things like that when I was a student? No. I mean, when I was first learning it, eventually I did. Like by high school, by middle school towards the end of middle school towards high school, I'm like, oh, okay, I think I'm beginning to get this, right? But in the beginning, I would just copy this number here from the balanced equation. Well, I didn't know. Okay, I didn't know. That's why I put the balance equation here, you know? I remember my past. I'm not ashamed of it. It's my legacy. It's part of the process, right? Okay, so nickel 2 chloride. Nickel, where is nickel? It's 58.7 plus 2 chlorines. 35.45 plus, oh, if I can hit the right key, 35.45. Okay, what do we have here? We have 129.6. Okay, finally we have everything set up. Mole of nickel 2 chloride cancels out, mole cancels out. So what we get is grams, right? Now they asked for milligrams. Don't worry about it. We'll get to that part. Let's first do our conversion and then we'll do that other part to get the actual answer. 0.503 times. Oh, I forget this. To keep this simple and keep it clean, I'm going to write, remember your answer here will be in grams of nickel 2 chloride, right? That's what we're looking for. Yep. But 1 in milligrams. Don't worry about that. Let me write the numbers down. 0.503 times, this is just 1, right? Times, this is just 1, times 129.6 grams of nickel 2 chloride. This explains why that's the answer, right? The unit is in that form. And then divided by 143.45 times 2. Okay, when you're plugging this in your computer, though, computer or calculator, at least if you have one like mine, I've seen someone whose calculator was very expensive. They could plug it in just like this and it will work out. For me, I have to write 0.503 times 1 times 1 times 129.6 divided by 143.45 divided by 2. If I say divided by this and then multiply by 2, my calculator brings this back up here and then doubles the answer, not the answer, but doubles the number that's present at that time, and I get the answer wrong. So this way I get 0.227 grams of nickel 2 chloride. Now they asked for milligrams. So now all I have to do is convert this to milligrams, right? So I go like 1 gram, 1,000 milligrams. So times 1,000, and I get 227 milligrams of nickel 2 chloride. Okay. So let's scroll back up and see what they have here. What did they get? Oh, they were still doing masses. They did they converted to millimole. I feel like this is a little bit more you know what? If you understand this, I don't want to take that away from you. You can do millimoles. I feel like that's a little bit more confusing, but they work it out and we get 227. Yeah, they work it out over here, and here they're just confirming. Okay. Okay. Now we're looking for percent yield. So let me give you a context. I'll tell you a story after I define these, okay? So ideal yield. Before we get into ideal yield, right? One of the things I learned, I've learned a lot of things about chemistry. Things that were communicated. Oh yeah, and then in chemistry, a lot of things are not communicated. That are important to understand chemistry. But one of the things I started to really understand from chemistry is in chemistry, everything, because it's a problem solving class, everything is viewed as a tool. Or at least for me, I started to view everything as a tool. A chemical formula was a tool, a definition was a tool. Not like difficult to work with tool, but like tools to help you solve problems, because this is a whole problem solving class, right? Even though we are trying to learn about the elements, but these chemical formulas, definitions, they are all tools to help us solve problems, right? And discover mysteries. Okay, so the mass to mass stoichiometry is able to be used as a tool to help us make predictions. So we can predict the future. Not the future of life, but the future of what we think will happen in a chemical reaction. We can predict an amount, not an occurrence, but we can predict how much should be made. So before we even define this, I'll say right here, mass to mass stoichiometry can, I shouldn't say can be because it's done, is used. See, nobody ever explained this to me. But we just did it. It was a thing that we just did. So what I did was I did what everybody else was doing. If they're doing it, you're doing it. You don't know why you're doing it, you're just doing it. And later on, I was looking back and reflecting. I realized, oh, we were doing this on purpose. You know what I mean? We were doing this because that's what you do. That's why we learned this. Mass to mass is used to predict the amount of product. So not just the amount of product, but I would say here the ideal amount. Now, some people call it not just the ideal amount, but the maximum. I've seen the term maximum amount of product that can be made. So on campus, what I'll do is, oh yeah, your lab. My bad, I forgot. I gave you guys that lab from on campus. Right. Before you do your last lab, the stoichiometry lab, you'll be doing some conversions, right? And before you actually start the experiment now, I gave you guys the data from the actual experiment. But what you would normally do is before you did the experiment, you did your own mass to mass stoichiometry. So you weighed your starting materials, your reactants, and then based on how much you had in your reactants, you were able to predict the ideal, the maximum amount of product that you should be able to make. And I told them, I mean, the mass to mass conversion gives you some level of power to predict not the future of the occurrence, but if you were to do the chemical reaction, how much product should you make, right? And the amount of product that you're predicting, not necessarily what really happens, okay? The amount of product ideally formed from the complete conversion of the given amount of reactant to product. So you say, I have a goal. My goal is to do a chemical reaction. I will use this amount of the reactants, and before I even go to do the experiment, I know exactly how much I should make. That amount that you know you should make based on mass to mass stoichiometry, that's the ideal. I usually say this is what's going to happen if everything is perfect, right? Nothing goes wrong. You don't mess up. You don't sneeze and drop half your sample. Your lab mate is not falling asleep on the job. You're not sloppy. Everything goes well. Everything is perfect. You make the ideal amount or ideal yield, okay? So once again, it's telling you here, you get this amount, so obtained from stoichiometry. They said it in so many different ways. This is just mass to mass conversion. Hold on just a second. Hold on just a second. Give me just a moment. I'm actually in the middle of the lecture right now. Hold on. Yeah. Sorry, I'm responding to one student who she was the one who actually asked me the to record this chapter, so she just sent me an email right now. Okay. So yeah, so they're telling you right here that you can get the ideal yield only from doing math, right? And then the actual. The actual is what really happens when you go into lab, right? So you're going into lab, you're doing so sometimes the actual is called experimental. I have seen books that refer to that experimental yield. So you go to lab. Now these ideal as your predictions, right? You're saying when I go there, this is what I should get. These are kind of your goals. Goals to get this. Actual is what actually happens when you get to the lab. You go to the lab, you do the experiment. That's what it's saying here. To get this number here, you measure it. You don't do math to get this. You measure it in the lab with the experiment or your experience. And then sometimes you get results from impure reactants, incomplete reactants, whatever. So this is telling you all the things that could go wrong, okay? Because this is real life. You go to the lab, your reactants were not pure, they're contaminated. You got some cheap reactants, okay? Sometimes you're impatient, you have incomplete reactions, or you got some side reactions, reactions that you did not expect to have, or you have human error. Okay, life happens. What do these do? These affect the quality and the amount of product. So this is the actual yield, what you make in the lab. Now, the goal is to make sure that the actual yield is equal to the ideal yield. But because of life and life being what it is, the actual yield is not always equal to the ideal yield. But for the most part, we expect the actual yield to be less, right? Because ideal is like the highest point, and then the actual will always be less than or at best at that high point. If your actual is more than the ideal, which is usually impossible, that just means your sample is wet. So it's extra heavy because of the moisture in there. But the target is the ideal, never above it. Well, how do we know your results are decent? Okay. Not as far as quality is concerned, but as far as the amount. Did you reach your target? How do we know? That's when percent yield comes in. So with the percent yield, remember the ideal was the target. It's kind of like a weight loss target, right? That's what I'm thinking about right now. It was the target. You wanted to lose 10 pounds, you lost 5. What percent did you lose, right? In this case here, back to the chemistry, you were trying to make 10 grams. You only made 5 grams. What's the percent yield? Okay. So I worked in this company one time where they were having us make a make a sample, and the job was not very challenging. Oh my goodness, it was so boring. I mean, once I was learning it, it was fine. Once I figured it out, I was like, oh, I need some challenge. So I called this other coworker and told her, you know what, I want to compete with you. She's looking at me like, we're at work, what are you talking about? I said, how about we compete to see who has the best percent yield? And she said, you know what, bring it on. I'm like, yeah, bring it on. Okay. And because the goal was to increase the yield to get it higher, we started to improve our craft and our technique, right? Minimizing all this error right here, doing better, showing up ready. And because I had to, make the job more interesting. So every day we will do our work, calculate our percent yield, and then compete. And whoever won for that day got to be queen for the day. And we had to do an award ceremony where I presented, the crown. It was more like a medal. It was something from the lab that we wrote on. Listen, you would think my boss would be angry because we're playing around. He called me to his office and said, ever since you came here, the quality of work has improved. He's referring to the percent yield. He didn't know we're competing. He didn't need to know. He's like, the quality of work from both of you has improved. I'm like, yeah. Thank you. Keep it up. I said, yeah. Queen for the day. Anyway, I had to keep it interesting, y'all. But hopefully you understand, right? That it's not just numbers. These numbers are communicating something. You have the ideal yield, the target. Okay? Okay, give me just a moment again. Give me just a moment. I will come back to this, okay? So I'll continue the lecture. Let me go ahead and address this. Just a moment. But yeah, we'll come back to that story. Where is this? Hold on. Okay, and where is the stop? Give me just a second and I will be back. Oh, why won't it show?